So next thing we need to talk about is efficiency and some of the diagrams that we use to express efficiency. The first thing the idea of efficiency, the work divided by the heat that's put into a system. You can hear the sirens, I'm sorry about that. Efficiency of any device is equal to the work that you get out of that device, divided by the amount of energy that's put in, if you will. And in this case, we're using Q because we're talking about thermal energy that's put into the device. So that's the general equation for efficiency. The other way we can look at efficiency is talking about reservoirs of energy. Okay, so when we talk about, well, let's take this one step further. I can also define work to be thermal energy that's put in minus any energy. Let me re-say that one. So this is the amount of thermal energy that's put in minus any thermal energy that leaves the system, that exits the system. This is the portion of the energy that's being removed. This is my work divided by the total energy that was put into the system. Okay? So this is a relationship that's giving my work. So the difference here is the amount of energy that's put in and the amount of thermal energy that leaves the system that isn't used. So the total amount divided by the amount that isn't used moving an object or lifting something is the amount of work that's done divided by the amount of energy that you put in. That gives me my efficiency. That gives me the percent efficiency that we're talking about. Okay? So the other way in which we can talk about efficiency is talking about reservoirs of thermal energy. When we talk about efficiency, and we want to talk about thermal energy, we talk about this relationship. Okay, so when we're talking about these, let me define some of this. 1 minus T cold. T cold is the exterior temperature. Okay, so a device is always in what's called a cold reservoir. It's the amount or it's the temperature outside of the device. So in the case of an engine, T cold is the atmosphere in which the engine is running. Whether it be cold, whether it be hot, that's the thermal, that's the reservoir. Divided by the hot reservoir. Now the hot reservoir is the actual device. So T cold would be the air around it. T hot would be the engine inside of that. Okay, so the thermal energy here, the thermal energy outside, 1 minus that gives me the amount of efficiency of a device running in a cold reservoir. Okay, well we can take that one step further by saying 1 is TH over TH, and we're left with TH minus T cold over TH is my efficiency equation. Okay, so that's an expression of efficiency. Now, looking at some efficiency, some devices and their efficiency. Let me grab my rag real quick. Okay, so using that idea, let's talk about a car. So a car has 100% of its original energy. Wow, that's not showing up at all. Dry my board real quick. Okay, so a car has 100% of its energy being plugged in. So the total amount of energy I'm starting off, well, right off the bat, 40% of that energy, okay, a big chunk of that energy, a total of, not 50, 40% of that energy is kicked out the back end of that car, okay, in the form of exhaust. As a matter of fact, if you put your hand over an exhaust pipe, it's an incredibly hot surface. You'll end up getting a serious burn. So please don't do that. So 100% out of that 100%, 40% of it is exhaust. Let me get the curtain going on. Is exhaust. Okay? Well, from there, 30% of it goes up towards heating the engine, and eventually it goes into, so 30% goes into the cooling. So you take the engine and you end up heating the coolant. So 30% of that energy goes towards the coolant. Okay? Another 5% goes into friction loss, moving parts. Okay? So you have moving parts that are in that system, and they create friction loss. So anytime two surfaces are rubbing against each other, there's energy there. And that energy is being turned into thermal energy, and it's not used at all. So that's friction. Leaving only 25% of that, no, not 25%. Yeah, 25%. Leaving 25% of that energy going towards the motion of the car, or turning on the lights, or playing the stereo. Okay? So if you look at it a different way, so imagine that you had 100%. Well, 40% of that goes into exhaust. Okay? 30% of that goes a little bit longer and goes into coolant. Okay? Another 5% of that goes into friction loss for the moving parts, where only 25% of the total energy being put in the system is used to move the car forward. So this is 25% efficient. 25% of that energy is used to move the car. 5% is turned into friction. 30% is turned into coolant, heating up the coolant. And then 40%, a big chunk of it, is simply pushed out of the exhaust. Okay? So that means that we have a 25% efficient car, which is actually fairly good. But in all honesty, that 25% eventually goes into friction loss, goes into resistance from air resistance, surface resistance between the tires and the road. Your tires heat up over time, heating up the brakes. Okay, so eventually that 25% gets converted into thermal energy at one point. So you can arguably say that 100% of my energy is lost. But the truth of the matter is we look at a typical car engine as being 25%. 25% of that energy is converted into useful energy, while the remaining 75% is trash. Okay? Now looking at another device that's efficient or has an efficiency that we can look at is a flashlight. Now you think a flashlight being efficient, it turns out the flashlight is even less efficient than the car engine. Okay, so with an incandescent light bulb, that's fairly true. So with an incandescent light bulb, you take a huge chunk. Here's my 100%. Right off the bat. Okay? Ooh, barely can see that. Right off the bat, 95% of that energy goes into thermal energy, heating up the filament and radiating out as thermal energy. We're only 5% is turned into light. Okay? So a huge chunk, 95%, is turned into thermal energy and is lost to the environment. Where 5% of that 100% is being converted into light. Okay? Massively inefficient. Now, we've gone on and made improvements. You can talk about the new compound fluorescent light bulbs that we put in, in the houses, or the new LEDs that we use for flashlights and for Christmas lights. Those LEDs they're called cold lights because they produce less thermal energy, and more energy gets turned into light energy. So the efficiency is actually increasing. So you can see why there's been a drastic change in the way in which we use energy in our household. If 95% of our energy is wasted by using a traditional incandescent light bulb, if we could just cut that down to 5%, or cut it down 5% to 90%, and generate 10% or 5% more energy in light, you've made a drastic change. Now, if you remember, if you look at your typical incandescent and you look at your compound fluorescent and the wattage that they require, the amount of power that they use or the amount of power, the joules per second, the 60-watt light bulb is only requiring 30 watts of energy typically. So it's about half. So that's meaning that your efficiency is not going to be 95%. It's producing the same amount of wattage or visible light, maybe even a tad bit more. So that means that your efficiency, the amount of energy that you're losing towards thermal, is got to be cut nearly, if not more, than half. Okay? So you're talking a 50% thermal loss and maybe a 50% light production. So that's why there's a drastic change, and why we can say changing a light bulb and buying a $5 incandescent or a $5 fluorescent is going to pay for itself, because more energy is being transformed into light energy and less energy being transformed into thermal. Well, our LEDs are even more efficient than that. Okay, so these are called Sankey diagrams, S-A-N-K-E-Y, and it's just a way in which we can do a graphical representation where this is the amount of useful energy or the intended energy outcome, and this portion right here is the wasted energy. Okay, cool. So that's a discussion of efficiency.